Okay, I just oh wait, what? No, Wi-Fi is not working. Oh, there's an extra credit for you guys if you can finish the teaching evaluation survey and send me a screenshot of the complete the notice, the window over there. Yeah, send it to the email. I'll give you a credit for homework 8. So we will cover a little bit of SRAM circuit today, and I think I missed a little bit of information for the course project that I will talk about. Let's go do this first. This is more important. So the overall logic of the circuit. Okay, we haven't talked about that yet, I think. So what is the workflow of it? So it's mainly explaining this part of the circuit, okay? It's confusing. This is the main logic of it. Okay. Okay, so the rest of the circuit is pretty simple, but now this is a control logic. For the control logic, just think about the procedure of the conversion of the start logic. Okay. What is this one doing? Clock SH. It's a sample and hold clock. Okay. So a rising edge will do what for this clock? Yeah, it will sample it. If we come back to the so you can see the sample and hold logic. You actually need a logic, the high logic 1 to sample it. Okay. And then you put it down to ground, it's going to hold it. So after it's being put down to ground, the conversion should start from here. You agree with that? Because it's a DC voltage being held over there. It's ready for the conversion. So we need to create a clock like this in the circuit. We have been doing the clock, which is 50% duty cycle. So we'll talk about how we generate this kind of clock in the circuit a little bit. Now let's come back to the control circuit again. All right, so for example, this is the sample and this is the hold, right? Okay. Then what about this one? So when it's being held, you hold this line to be 1. Okay, and why is that? Let's come back to the, I think that's a sequencer or logic register circuit. Not this one. I think it's the one on the top. This one. Okay, so that line is directly connected to this. And if you look at the label here, they are all shorted together from here to here. All right. So if I give this pin a 0, what's going to happen? So see this, and this, they're all shorted together. If I give a 1 to this line, what's happening to this sequencer, I think? Wait, just confused about the name of these two part of the circuit. But what for the top row of the circuit, if I give a 1 here, what's going to happen? If I give a 0, what's going to happen? Yes, low active. Yeah, so because this circuit, I use the TI T flip-flops. They're all NAND gates, right? So it's 0 active. 0 active, if I give a 0, put a 0, you can see this is S, right? If I put a 0 here, it's setting this one. Okay? It is setting this one and resetting the rest. If I put a 0 here. Okay, so it's basically giving a 1 here and 0s to the rest. Okay? But because zero active, so we are actually using the Q0 instead of Q, but it's just a resetting cycle. If I give a 0, it's resetting everything and giving you a 1 and all zeros as a start. So if you try to recall the process of the start logic, you start with what? The very first state is what? Number. Can you still remember that? Remember how we do the start logic, all the conversion? Yeah, one all zeros, right? Yeah, so the first cycle you have one, if it's a four-bit converter, then it's going to be 1 zeros and then start the conversion. So that's, you need a reset cycle to reach this kind of state for the logic register over there, right? So that's what the reset doing. You need that one to start the conversion of that cycle. So when do you want to start the conversion? When would you like to start the conversion? The SAR logic, the SAR functional block is actually the circuit doing the conversion, right? Working with the comparator to finish all the conversions. The SAR logic. So you reset it, then you want to start the conversion. So when do we want to reset it and start the conversion? That's right. So when it's holding, you want to start the conversion. And so now we want to start design the control logic here, right? So when you put it down to 0, you reset it, but at the same time you sample it. And after that very short period, you don't need this one to be very wide, right? You don't want a 50% duty cycle. It's a waste of time. You just reset it, give a logic 0, it's get the work down, and then you just want to move forward. Same to the sample and hold. You sample, you hold it. Okay, you can actually make this one narrower, but this is just a concept of the cycle. Okay, so we reset it, you get all the 1 and all zeros ready over there. Okay, so 1 all zeros over there is ready, and then you right after that you hold the voltage, and then it starts to the conversions. Okay, during this period. All right, so when the conversion is done, you come back to the overall circuit, look at the main block of the circuit. So this is the output of the SAR, right? So it has all the intermediate values from 1s, all zeros, and until the final result. If it's an 8-bit ADC, you need 9 cycles. So after the 9th cycle, you are having the final result, but all the previous ones are just intermediate values. They are not completed yet. So you need at least 9 clock cycles in order to get the final result. So you want to wait until you have a final result, maybe at the 10th cycle. I mean, at the 9th cycle, right at the rising edge, you are getting the final result, but we want to send it out at the same rising edge. I'm not sure, actually. Maybe not a good idea. So what if you wait until the 9th cycle, right? After the 9th rising edge, the data is already available there. So what if you run another clock? Is it going to change the value here if you run one more cycle? So remember, so now we just come back to the diagram, right? So this one is being shifted to the right, okay? And we are adding the comparator's result in the front. Right before the final stage or final state, you are having whatever, right? And a 1, which is this one. So this will be A3, A2, A1, and eventually you have A3, A2, A1, A0, right? These are all the comparator's output. That's the final result. Okay, so if this is the final state, and what if you run one more cycle, what's going to happen? Is it going to stay in the same at the same value, or it's going to change a little bit? Because we know this is the final result. This is the result we want to use. So what if we run it for one more cycle? What's going to happen? So let's come back to this digital circuit and look at it. So it's going to be the sequencer thing, right? So for example, now we have all the final result being displayed at out 7, out 6, out 5, out 4, out 3, out 2, out 1, out 0, okay? As the final result. So if you run it for one more cycle, what's going to happen? So we're remember on the from the top, right? It's shifting the 1 to the right. So it's setting each bit in a certain sequence in order to provide a rising edge to the clock for the previous stage, right? But because it's zero active, it's basically all zeros and only all ones, but only 1 0 appear at one diffie flop in order to set it. It's a zero active. It's a setting it, right? So setting it is providing a 1. The 1 will provide a rising edge for the clock. Okay, does that make sense? No? Sorry. It's been a while. So when the data is done, right? So if it's an 8-bit ADC, you need the 9 cycles. Okay. You need the 9. So yes. So the reset is counted as the first cycle, actually, right? So after the one is like moved through all the positions, what would happen? Yeah, after you get the final result here already, right? Okay. The reason we need the one more cycle is because because we are using the same clock, there's just one clock. At the rising edge of the clock, it's going to do something at the same time. So at the 9th rising edge of the clock, we are having the final result. There will be a little bit time delay, but at the 9th cycle, you are expecting to have the final result over here. So the correct digits will appear here. Okay, but at the same time, do you want to kick it out by using the same clock? See here, this is a parallel in, parallel out flip-flop array. At the 9th cycle, the clock will, the rising edge of the original clock, which is here, which one we're using? This clock, okay? This clock to the star ADC will have your 9-digit or 8-bit binary final result ready. Okay, do we want to use the same rising edge to kick it out? Or do we want to use the same rising edge to kick it out to the final output? This is just a latch, okay? It's an 8-bit parallel in, parallel out. Just a parallel in, boom, get in. But you need a clock to trigger it, to send it over to here. It's a D flip-flop to register everything. You need to wait until you have a final result. You don't want to send out all the intermediate values, right? Okay, so now the question is, when do we want to kick it out? You know what I mean? If you kick it out at a different time, at the wrong time, you are having some little errors for the final output, and the eventual accuracy of the ADC will be decreased. Well, you need to kick it out before the transition to the what? So yeah, good point. So the question is, after the 9th cycle, okay, we're getting the final result. Do we need to kick it out as soon as possible, or it doesn't matter? I mean, if there, for example, it runs for like 10, 11, 12 cycles, is the value going to change or not? Think about this very quick. Is it going to change? It's a question we haven't thought about before. So for the SAR logic, right? On the paper, we know we run it, we reset it, and we run it for another 4 cycles. Counting the first one, we're having 5 states, and the very last one will be the final result. On the paper, it's okay. We just stop here. Okay. What about in the digital circuit? What if it keeps doing this comparison and keep running? What's going to happen based on the physical circuit here? Actually, the sequencer and logic register here. What's going to happen? Why? So that little one will be shifted out, right? And you don't have that little one anymore. Yes. All zeros. Then what's happening to the bottom D flip-flops? Because these are the D flip-flops holding the data here, the final result, right? And now if it's not having any rising edge happen to any of the D flip-flop anymore, what's happening to it? Yeah, it's memory. It's going to memorize all the final state. It's not going to change anything until the next reset. So it's actually okay, right? You can wait until whatever, like 100 cycles is still the final result. They're not changing it. But we don't want to wait that long because we want to make the ADC faster. So if you don't know if the 9th cycle will be the right one to use, we can wait until the 10th cycle, actually. I don't have an answer for you, but I think the 10th probably works. But let's come back to the block, okay, the overall block here. So this clock, which is the rising edge to kick it out, right? Definitely cannot be the clock here. This clock, original clock for the SAR, is a 50% duty cycle, is a regular square wave. Is that correct? So let's come back to this one. So the clock, do we have a clock here? Is there a clock? Here, right? Yeah. So for this clock, do we need to modify it? Or just use a 50% duty cycle square wave? In our simulation, I didn't modify it, right? Do we need to modify it? I don't think so. It's just the original clock driving the D flip-flops on the top in order to do the shifts, right? So this clock defines the speed of the conversion, right? How fast you are transitioning from in between all the states. You have 9 states, right? So this one is just 50% duty cycle square wave. You don't have to change it. So every clock over there is just a regular clock. So every clock over there will change the state to the next state. So which means that clock is like triggering or making all the transitions happen in between all the states. Okay, moving the states from left to right. Can we use this clock for this clock? For this door clock? Do we want to synchronize it? Like this clock is doing all the conversions. Every clock will trigger one state here over here. We'll update the state. And can we use this clock for the door clock? Why and why not? All the intermediate states, right? Yeah. So what you want to do to that clock? Yeah, 8 times, 9 times slower, 10 times slower, right? So you're gonna wait until the ninth of it, then send out the rising edge. Okay, so what is that circuit called? How can you make it happen? How do you modify it? Mm-mm. It's basically like you have the original clock for the SAR, right? The SAR is doing all the conversions like this, right? Until the exact number you want, you okay, and then keep doing it. Agree with that? So that's the door clock. So when the conversion is done, you kick it out. How do you make that happen? Just a counter. So count until 9 or 10, you trigger it. Okay? Just a very simple counter circuit. How do you design a counter? Here's a counter. There are so many circuits to design a counter. So for example, this one, okay? So this is a regular counter circuit. It has the original clock. Count from 0 to 1, 2, 3, 4, 5, 6, 7, 8, whatever. So it's just a regular counter counting one by one each time. And outputs Q1, Q2, Q3, Q4, okay? And I need, if I want this counter to count until 1010, what is 1010? 10. If I want it count until 10 and reset it, because this original counter cannot count until 10, it just keep counting upwards until 1111, right? That's a maximum number, and then it's gonna reset because it doesn't have another register following. So it's doesn't have a carry out. It just reset to all zeros after 1111, all right? But we don't want to count until 1111, which is too big. We just want to stop at 10, right? How do we make that happen? So I have to design a little bit of combinational circuit here. See, if I have 1010, I just need to add an inverter in front of the 0 bit, okay, to make it all ones. And then the AND logic, AND gate will do the selection. If it's all ones, I just output a 0 here. You know what I mean? Since you have all ones here, it has to be all ones in order to make the output of the AND gate to be a 1. If one of the bit is 0, you are not getting a 1 here. Okay, if you are not getting a 1 here, you are getting a 0 here, you are getting a 1 for the NAND gate. You know what I mean? How to design this combinational logic? It's very simple. It's let me see how to design it. I mean, just thinking about the digital circuit, it's without following a certain routine, it could be difficult, right? But how to design it? Yeah, Q4, Q3, Q2, Q1. So it's providing some guidance to it. 1010, and for this is digital circuit, right? Digital circuit. 4 is a 4-bit input and 1-bit output. Okay? And that's the only output I need a 1 for it. Do we need a 1? Do we need 0? Sorry. 0. And we have to invert it to make a 1. It doesn't matter, it just invert it, right, eventually. So let's say, let's just give an example here so we can figure out the rest. Okay? 4 input, 1 output, and we need to design the digital circuit to implement this function. How do we do that? How many combinations do we have? 16, right? You just list all the 16 input, and all the rest should be 0, but only this one should be 1. Okay? But do you care about all the zeros? You don't. You just look at the 1. So you are getting Q4, Q3 not, Q2, Q1 not. What is this? Don't overthink it, okay? Don't make it complicated. This is just the logic 101. Logic 101. You got 4 input, and what we need is whenever it reaches this input pattern, I need a 1 for the output, but all the rest, I don't want to trigger it. Just give a 0 to it. Same concept if you are accepting a 0, but all the rest is 1. You just use a different way to do it. Now, for example, we need this pattern to get a 1. Okay, that's the truth table. And from the truth table, we can find the logic function. And from the logic function, we can find out the digital circuit, right? So what is the digital circuit? Already tells you that's the AND gate, AND gate, AND gate, inverter, inverter, right? So I have Q4, Q3, Q2, Q1. Q3 has to be inverted. Q1 has to be inverted. And all the output are being ANDed, right? And then ANDed one more time. So it's gonna send you a 1 out only when you have this pattern here. And you can use this one to reset the counter. So when the counter reaches this one, you reset it, it's gonna go back to zeros. So it's not reaching 1111. It's reaching like 1010, then it's gonna be reset with all zeros. That's how you design a counter to count to a certain value. Okay. Because this is a circuit I designed based on the truth table, and that's how I did it, like this. Okay. There are some modifications because some of the circuits are zero active, so I have to modify some of the gates really quick. But you can see a NAND gate inverter, it's just an AND gate. Okay. You combine these two together, it's just an AND gate. I split it so I can get a 0 in here for some zero active D flip-flops. Okay. Okay. So in this example, I'm counting to 10, and this one counts to 9. So seems like the door logic, the door D flip-flop is using the 9th clock to send it out. You could change it. I mean, to 10, I'm not seeing a significant difference, but I'm assuming it will be ready. But I probably have to zoom in to the waveform to look at the data, see if it's really ready over there. You know, this may decrease the accuracy of the ADC, but assuming that it's going to work to some extent. So I'm using the 9th cycle for the door clock. Okay, so the 9th cycle will kick this out, right? So what are the other clocks that we need? So see, there's a clock reset, there's a clock of sample and hold, right? So we were talking about the sample and hold. It doesn't have to be 50% duty cycle. So I'm using this kind of counter circuit to create all these pulses to do whatever we want. Seems like this will happen the earliest. So the 9th cycle, it will send it out, right? So what's after that? So we send it out. We got a pulse to send it out, right? Then we are done. We're done for the data collection. So what's next? It should get it ready for the next, right? You need to reset the SAR. That's right. So reset the SAR, you see here, clock reset, SAR set reset. So seems like at the 9th cycle, I send it out, and at the 10th cycle, I'm using a zero active over here to set the SAR again to make it ready for the next, which is reasonable, right? The data is ready, I kick it out, then I just reset it for the next at the 10th. So the 10th cycle, if you, so that's the SARS set and reset. But now let's come back to the diagram we drew in the picture. This one. Okay, so when we design it to be like that, right? So when the SAR is resetting it, giving a 0, we just invert it. So seems like the clock of the sample and hold just need to be the inverse of the SAR reset, right? So just simply invert it, right? Okay, so that's why I have this one to be the sample and hold clock. It's very interesting. So we actually started from here. We are not start from the conversion, but we start from the when we finish the conversion, assuming it's done, right? And then we start the next. So the 9th cycle will kick it out, and the 10th cycle will reset it, and at the same time do the sample and hold. Okay, and now you can see this is even after this. This is 10, this is 11. So what is this doing? So this comes to 11. And 11 is giving a 0 out, right? So clock reset, what is that? Clock reset. I think so too, but let's look at it. Where is that clock reset connected to from the original? Clock reset. Do we use it? Oh, it's, wait. Okay, so it's resetting the counter. Make sense? We don't want to count until 15, right? Because the counter is counting, and we still need the counter to count until, like in this example, right? We needed to count to 10, to 9 to 10. We still needed to keep counting up. But after 10, seems like we don't need it anymore. If you don't reset it, it's going to keep going up to 15, right? So that's why we reset it at the 11th cycle. Do you want to reset it at the 10th cycle? So the 10th, so the 10th is providing a clock here, right? It may work, but just be safe. Let's just count one more time. It's not affecting anything, right? Okay, so at the 11th cycle, we reset the counter. So if you see clock reset, I believe it's connected to here, see? That's all the D flip-flops of the counter. So it's gonna wait, it's a zero active. So it's setting it, but we are using Q bar, so it's actually giving zeros to everything, right? Or even though we are using Q, but we invert it, right? So eventually it's still 0. So after this one is getting set, Q is going to output a 1, it's going to invert it, it's outputting a 0. So all the outputs of the counter become zeros. So the counter will start from 0 and keep counting up after that. You can try it actually. Since it's a circuit just have. As long as the counter signal gets out before. Counter Yeah, the result gets up. Yeah, the result is out after the ninth, right? It's right there. So I don't know why we cannot use 10. Yeah. So we at 10, we are getting these two pulses, right? So at the 10th, if we do the same thing, then these pulses are gone, will not be there. So I should have to wait, right? Oh, yeah. How do you make the time delay? Mm. Mm. Yeah, yeah, that's right. But why don't we? Hmm, that's right. It's a little thing to tweak, right? It may speed it up, but this may be safer, right? So it's easier and safer. But I don't know. There are a lot of things to be changed over there. Understand it? Yeah, yeah, yeah. So 11 will reset everything, and okay, okay. So the counter is reset. Counter is reset to all zeros, and um, I believe it's just starting another cycle because you are getting a reset of the SAR signal, which will give a one and all zeros for your sequencer and digit register to start with. Okay, so it's going to start another cycle. So this may not be the perfect design, but it worked to some extent. Okay, it does give you a sine wave, and the first cycle, you turn on the ADC, your music signal comes in. That's just exactly just the first cycle. It's just first period of your music signal. You keep it on, there are just millions or thousands of at least of waves after that. So you are seeing a huge dip over here. You are concerning like ADC is not working properly. No, it's just you turn on the first time, everything's getting reset. You are expecting, the very first digit or the first data is not whatever you expected. When you turn on the music, you do hear some of the uh, surges. I don't know. You can figure it out eventually, but you don't care. You know what I mean? Who cares about the first 1 millisecond of the music? It's not whatever you want to listen to, right? Nobody cares. You turn it on, you just keep going, right? I don't know actually. Um, you can add a filter to remove it. It's not a big deal. Just add a low pass filter. This is just a raw signal of the DAC, and uh, you need a lot of filtering circuits to make your music sounds better. I think. Don't worry about that. So it's following the sine wave, um, and this took how long? 30 minutes for my computer to run just one period of sine wave. That's ridiculous. So if you can repeat a sine wave, okay, you'll get full credit. Make sense? It should be pretty simple, I think. So for the comparator, you can use a comparator from the example. I think I have one package over here from the textbook from Dr. Baker's. This one, or you can use this design files that I do have a simpler version of the biasing circuit of the op-amp. You can use that one as well. It's just providing a DC biasing voltage for the gates of the op-amp. And either one works, okay? But the one in my design simplifies things a lot. If you want to use that one, it works. Okay, is that clear? It's a pretty exciting project, right? You can get a sine wave recovered. Any questions? See the biasing circuit is providing a biasing N, balancing P for this. VGS equals, so IDS equals VGS minus VTHN square times blah, blah, that thing, right? So you need a gate voltage to provide an ID for all the circuits. That's why you need a biasing circuit, biasing. But you need to turn it on. You know what I mean? You need to turn it on. So this is the voltage to turn it on. So for the original design from the textbook, it has a little startup circuit. It's not oscillator, but it's because of the not balanced transistors. It will start up by itself and keep charging up some of the transistors and eventually stabilized at one state, providing all the DC circuits designed in a way to make it happen. But I think in my design over here, it simplifies things a lot, which changes the biasing voltage eventually. The only thing is it has a different VDD, right? You may have to, I don't know, the voltage of the, let me see. As long as you can turn it on. Okay, so let's do this. Because the design in here from the textbook is based on C5, right? It's a 5 volts VDD, and we are doing C5 as well. So you can refer to the voltage being generated over here. So you probe the voltage of the gates and you find out the voltage that you want, right? So what if let's just use whatever in here. What about that? Okay. It's C5, it's op-amp, it works, even though the biasing circuit is a little bit more complicated. We're not doing the layout. All right, let's just use it. There are different versions. I think there's a 2-stage, 3-stage. Just pick up one of them. I think the 2-stage one, the standard one, and use it. You don't have to modify anything, just copy and paste to your design. Okay? Make things easier. Okay. We'll talk about the memory circuit really quick. Yeah, I've heard about SRAM, or the terms, the jargon. What is SRAM? No, actually. Yeah, static RAM. What is RAM? Random access memory. Okay, what is DRAM? Dynamic random access memory. So what is SDRAM? Yeah, that's a synchronous one. That's right. Wait, SDRAM. Yeah, it's a synchronous. Synchronous what? Yeah, DRAM. So SDRAM is a DRAM. Let's see. Why do we have so many different memories? There are all with different circuit design, right? There are different circuits. And there's another memory called E2P-ROM or flash. Sometimes you'll see flash. It's very, it's a newer version of the E2P-ROM. Yeah, there are all different types of memory. Writable, programmable, not programmable. It's a read-only memory. It's a read-only memory. You have to use a charge pump to boost the voltage to 20 volts in order to write into the memory. So that's where you need a charge pump. If you find a circuit design job in Micron, in Boise, wait, that's a memory company, right? Biggest in the world right now. So if you find a job over there, probably the interview question will be to design a charge pump circuit, or they'll ask you how to design the charge pump. Yeah, I did it. I drew it, and also you have a charge pump circuit on the in the textbook, right? So you need to boost the voltage to 20 volts in order to write it. We don't have the time to show the detail of the circuit anymore. So we'll just focus on SRAM circuit. So SRAM is being used for cache. If you have taken computer architecture, you probably have learned cache. It's a very fast memory, but it's very expensive. So you cannot use SRAM to build a memory for the SD card usually, or the DRAM, the SRAM for the memory for the RAM memory for the computer, right? Have like a lot of gigabytes over there. So usually they are small but fast. So being used for the memory next to the CPU, and they are called cache. It's fast and expensive. So circuit looks like the following. For example, SRAM the read process. Oh, sorry, just one. Okay. Yeah, Dr. Baker is a memory expert. He was a department head in Boise State University, which is just next to Micron, and they have a lot of collaboration between the campus and the department and the company. So they have sent a lot of students, and one of them right now is probably the principal engineer in Micron. I believe some of the DRAM you have in the computer is probably from his students. And he has over many years ago, I was looking at his profile. He has over 160 patents on memory design, just all DRAM stuff. So I believe every single one's memory circuit, memory chip on your smartphone or computer or laptop has a lot of circuit design from Dr. Baker and his students. And this is the fundamental circuit of the SRAM. This is called a word line. This is called bit. So this is bit bar. And there's a clock to control it. So that's a read process. That's a read process. We probably don't have time to run it right, but this is a read. So the reason we need a PMOS to charge this point to VDD eventually and why is that? So when we are reading, so for this kind of circuit, we talk about it on Wednesday. What is the difference between this one and this one? What's the difference? So that's the inverter input of this inverter, right? They are shorted to this pin this way, but it's just basically just the inverter's input. Okay, so that's the first inverter's input connected to the second inverter's output, right? And this is a second inverter's input connected to the first inverter's output. So it's input to output, input to output. What's the difference? Input to output, input to output. What's the difference? No difference. The same circuit, just trying to confuse you. So it's whatever in here is just a latch. It's just a latch. Okay. So the latch is going to store the data over there as a memory. And if you have 0, this must be 1 because it's being inverted. Okay, and this is very stable. So during the read process, these NMOSes will be turned on. But before that, we need to charge this point to VDD, charge it to VDD, and we shut it down after that. So it's because we need a 0 to turn on the PMOS. So it was on and then turn it off. So what this one does is it's going to charge this up to VDD, and then when you turn off the PMOS, this point becomes a floating VDD, right? Becomes a floating VDD. Why do we need a floating VDD for it? I'm asking this question: is this 0 stored in the latch? Is this 0 a strong 0 or floating 0? No, this 0 is strong 0. It's a latch. The inverters are on and grounded. It's being stored over here. It's not floating. It's shorted to the channel, to the ground, right? Because this is on. It's a very strong 0. And this is a floating VDD or strong VDD. You turn it off afterwards, right? It's a strong VDD or floating VDD. It's a floating VDD. Okay. When during the cycle that I'm reading from this line from bit, okay, if I turn on this word line, the two NMOSes are on. This one will be discharged as a strong 0. Am I reading a 0 or 1 for here? Am I reading a 0 or 1? I'm reading a 0. And I do have a 0 stored here, so I'm reading a 0, which is correct. Okay, so what if I have a 1? So what if I had a 1 here stored over here? What's going to happen? I had a floating VDD, and if I turn it on, this transistor is on. So I see a 1 here, I see a VDD here. It's not changing. The potential is the same, so doesn't have any current flowing through it. Okay, so I'm reading a VDD here. The reason that I need to pre-charge it to a floating VDD is because NMOSes are good at passing zeros but not ones. If I'm reading a 1 here, I just don't want to read a VDD minus VTHN over here. You know what I mean? So that's why we pre-charge it to VDD. Just need to understand to this point, I think. Okay. So next week we'll start working on. It just finished. To try to finish up all the assignments. I think the project. I removed one of the home assignments. I think there's just one more home assignment. You need to return it, give it to me. But other than that, it's just the final exam next week. The week after next.